Hello, it's Darasa Online again, and today we'll be discussing advanced mathematics, doing some few revision on advanced mathematics, and the topic today will be differentiation, especially in application of differentiation. And today we are going to cover something known as, Taylor's series and the Maclaurin series, and you will be with Mr. Kimati, your teacher today. Let's see what it looks like. Now we shall cover the following. First of all, we shall see what is Taylor theorem, and we shall define some few terms there if they are few terms to define. And then after that we shall find the derivation and examples of Taylor's series, or Taylor theorem, or Taylor's expression, as other books do write. And then after that we shall deduce Maclaurin series as a special case of Taylor theorem. And then after that we shall find some few applications, or we shall use this Taylor series and the Maclaurians to find and expand expressions, and to find some values if there are values to find. And then after that I will leave you some few questions for you to practice. Let's go on and see what is all about. If f of x is a function that can be expanded in ascending powers of x, then the series f of x can be written as follows. That means is a summation of what? A summation of this factor, that is c sub I, in brackets x minus a raised to I. That is to say, it starts from when I is equal to 0 to infinity. That is to say, when we put a 0 there, that means there will be 0. That means that factor will be a 1 times c sub naught. It will remain c sub naught. And then when we put 1 there, that factor will come up. And then when we put a 2 where I is, that factor will come up. And let's see. That is of what? Of a c of I when x minus a raised to I. And I starts from where? Starts from 0 to infinity. And this, that means, is say we have a c of naught, as I've said earlier. Then we have a c1. Then a c1, this is multiplied by x minus a. Then plus what? Plus a c2, x minus a raised to 2, plus a c3, x minus a raised to 3. Let's say end up there, x minus a raised to 4, down to when it is infinite. So let's find those values. Let's find those values of what? Of c naught, c1, c2, and so on and so on, and see how will it look like. Now as I've said earlier, that we shall find those values when x is equal to a. Now check it out very much correctly. If you put x is equal to a there, that is to say this term will be equal to 0, and that will be equal to 0, and that equal to 0, and that also equal to 0. That is to say we have f of x equal to that thing, and that is to say I want to put there a, sorry, that will be a. That will say we are going to have a c naught. Now let's go on and find the value of the other values. Now let's differentiate that. That is to say we differentiate this, and this is just a constant. Remember, these are the constant that we are trying to look their values. So let's differentiate. If you differentiate a constant, we know it's 0. And what about that? If we differentiate that, this is our expression there is raised to 1 with respect to x. That means we are going to have a c1 plus what? If you differentiate that thing there, we are going to have a 2 c2 x minus a, plus differentiating that is 3 c3 x minus a raised to 2. Then plus what? Differentiating that, we have a 4 c sub 4 x minus a raised to 3, plus down to so forth. Now what will happen if we try to put the value of x there equals to a? That is to say this one will go, and that one will go also, and that one will go also. So that is of a equals to what? Equals to a c sub 1. So we have obtained the value of c sub naught, And now we have obtained the value of c sub 1. Now let's check the other values. That means let's go on and differentiating this one to the second derivative. So differentiating that to second derivative, that means this is the constant, will go, and we will be left with that 2 c2. Then this, remember, is raised to 1. That means it will be equals to a 1, and plus this one, it will be 3 times what? Times 2 c sub 3 x minus a raised to 1. That means we can write it there, or you can write it just to remind yourself. And then we have a 4 times 3 c sub 4 x minus a, and so forth. Sorry, there is 2. So what will happen if we try to find the second derivative? When we try to find this value, remember we are trying to put a in terms of x. That is to say, all of these will go and we'll be left with this one, that is 2 c2. So remember, we are trying to look for the value of c sub 2. That is to say, it implies c2 equals to second derivative of that evaluated at a over 2. Now we have obtained the value of the second constant. Let's check if we obtain the value of the third constant. Now we go back there and we differentiate again to third derivative. That is to say, the third derivative of the function x. So this is the constant, will go, and that one will be what? Will be 3 times 2 c sub 3. Remember, this one is a variable and raised to 1. When differentiated equals to 1. That is to say, it will be plus what? A 4 times 3 times 2. Sorry. Times 2 c sub 4 x minus a raised to 1, and we can let's leave it like that, and it goes on. Now let's evaluate this at x is equal to a, though therefore we are going to have something like that. All of these will go, and this, if you try to look that much careful, you will find it is 3 times 2 c sub 2. That implies the value of c sub 3, c sub 3, the value of that will be of a, and if you try to look that much careful, if we multiply by 1 there, it's still the same. That is to say, we can say this is 3 factorial. I do hope you do remember that. So that means the value of c sub 3 is equal to the function, the third derivative of this function evaluated at a over 3 factorial. Now let's check the value of c sub 4. So that means we are going to find the derivative of that equation there, the fourth derivative. That is to say, we are going to have the following. We have this sub 4. I'm trying to denote that as the derivative of that function. So this will go, and we'll be left with this one. That is to say, we are going to be left with 4 times 3 times 2, and this one can go there. That is times, there is c sub 4, and plus other terms. And if we try to deduce the other term there, you can deduce the other term, though we didn't write it in the first place. Let's check how will it look like. It will be a 5. Just practice this. A times 4 times 3 times 2, then times what? A c sub 5, then x minus a, plus so forth, Now, what is the value when we evaluate that equation when x is equal to a? Because we are trying to do that. So, if try to do that, all of that will go. That means we will be left with this. And if you try to look that much careful, you will see that is just a 4 factorial of what? Of times c, that way. And this implies a c sub 4 equals to the fourth derivative of that expression from the definition evaluated at a over 4 factorial. Now, remember, this was the expression that we were looking for. That is to say, we are going to replace these c's by the values that we are obtaining there. So what equation will be left with? So we are going to have f of x equals to what? Equals to this one. So c sub naught is f sub f of a. So we have f of a plus, what is c of 1? C of 1 is f dash of a. That means it's the first derivative of the expression evaluated at a. That is, but remember, this one is multiplied by that expression there. That is to say, we are going to multiply by what? We are going to multiply by x minus a, this one. Okay, plus what? The value of c2. Where is c2? Oh, yeah. C2, this one. Sorry, this one. So we have C2, and C2, the value of it is f dash dash of a over 2, and that is multiplied by a minus x, x minus a. Then let's go on. What about the third one? That is to say, we are going to have a c. Oh, sorry. The third derivative, this was the second. The third one, this one. So we have the third evaluated at a of over 3 factorial x minus a plus the next one. We have that one. That is the fourth one. So we have this one of 4. In other books, they write a 4 like that, but they put this way, so as to denote the derivative, the fourth derivative of the function. Or in other books, it does write Roman 4. So this evaluated at a over 4 factorial multiplied by x minus a. And remember, try to remember, this one was raised to 1, and this one was raised to 2, and this one was raised to 3, and this one will be raised to 4. And that is to say, if we try to write the next term from this, it will be denoting the derivative of a over 5 factorial times what? X minus a raised to 5 plus down to when I is equal to infinite. When I is equal to infinite. Now let's for example, if we let h equals to x minus a. So what will be the value of a? What will be the value of a? Let's make the subject, it implies that a is equal to x minus h. X minus h, putting that to that side and this to that side, I think that will be the correct. So let's replace this by h. Let's place this by h. We shall use this as we do questions. I will elaborate somewhere. As we do some questions, I will elaborate how it is used. That is to say, we are going to have the following. If we replace this term x minus a by h, what are we going to have? We are going to have the following. F of x equals to f of a plus f. We have a h there because we are trying to replace that. So let's write a h before f dash of h. H plus, so some other books, or sometimes you can just write this is by over 1 factorial. Then we have a h square, second derivative of the function evaluated at a over over 2. Then we have h raised to 3, f dash dash of a over 3 plus h raised to 4, the fourth derivative. So it goes on of a over 4 factorial and so forth and so forth and so forth. So this is what is so called a Taylor's series, or Taylor's expression, or Taylor's expansion. This is how it is found. So we have from the definition, that one. So you go on finding the values of c, then you find the derivatives up to when you reach at that point. Or in other books, they just reach at that point, and it is very, very much correct. So this is what was required, and then we have obtained that. I will explain this as we go on. That means the value of x there is equal to a plus h. I will explain it as we go on, doing some few questions later on. So you'll find that this is so-called Taylor's expression, or Taylor's series, or Taylor's expansion. Now let's see how in this can it be applied when we are trying to solve some few questions. Now let's see how can we apply this when we are trying to solve some few questions. Let's see it. Now examples. Now example on Taylor's series. That is to say, use the Taylor series to expand sine of pi over 6 plus h in ascending powers of h as far as the term h raised to 4, and hence find the value of sine 31 into four significant figures. So we are told to find the expansion of that using Taylor's as far as h raised to 4. That means we shall see how it goes up to when h is equal to raised to 4. That is to say, we are supposed to end up at that point. H will be equal to 4. So we will see how will it look like. So let's see how we do this. Okay, now let's go on. Now we have sine of pi over 6. We have a sine of pi. Now we have sine pi over 6 plus h. Now we have to expand it in ascending powers. That means when we say ascending powers, we start when h is equal to 0, and we know that is 1. And when h is equal to 1, that is h. When h is equal to 2, we will go on. That is to say, we are going to use something like that. So we are going to use that series to find our expression in this equation. Now we have sine of pi over 6 plus h. Sine of pi plus 6 sine of pi over 6 plus h. Now how are we going to do this? Remember, our series is like this. F of x equals to what? Equals to f of a plus f dash of a. Then we have h. Remember, there is a h. We have h square f dash of a over 2 factorial. There sometimes it's written over 1 factorial, which equal to 1. Then plus h raised to 3, the derivative of a over 3 factorial, h raised to 4 over 4 factorial. Now this goes on. That's why in our question we have been instructed to find as h goes to 4, and then after that we have been told to find the value of sine 31. This is in degrees, remember that. This is in degrees. Now how are we going to do that? And this is our series, how it will look like. Now remember, I told you as I was explaining how we expand, we said that this is equal to what? F of x. I wrote, if I did that much correct, plus, it will be a plus h. That means our x is equal to a plus h. And if you try to observe that much careful, it's the thing that is on that place. So trying to equate that, you will see that trying to equate this with pi over 6 plus h, our a will be equal to what? To pi over 6. That means we are going to evaluate the values of a when pi is equal to we are going to evaluate the value of that function when a is equal to pi over 6, and our function will be like that. So this is our f of x. That is our f of x. Now let's go on. So I do hope you remember this, and it's a good reminder to you. Now let's see. Our function is f of x is equal to sine of what? Sine of x. And what is our x? And what is our x? We are going to evaluate when x is equal to a. And a, we are going to evaluate when x is equal to a. We did in the last part. And what is a? Our a now is pi over 6. That is to say, it implies we are going to find the value of sine, of what? Let me write that much correct so that we can understand each other. Of a. And what is our a? Our a is pi over 6. That is to say, we are going to evaluate when sine is equal to pi over 6. And we know that the value of sine of pi over 6 is a half. That is of no doubt. Now let's go on and do the second one. That is to say, we are going to find the value of that, and so forth. And then we write that expression in that expression. So let's have this. The derivative of this. It is cos x, and it implies when we try to evaluate the derivative, and when we try to evaluate the derivative like that of a, what are we going to have? We're going to have the following. We're going to have cos of a, which is pi over 6. And we know that f of a will be equal to what? Equals to under 3 over 2. Now let's go on. Let's go on. We know this, we are at that point. What about that point and that point? Let's have the second derivative of this. We know that when we differentiate, cos of x equals what? Negative sine x. And evaluating that equals what? Equals to negative sine of what? Negative sine of pi over 6, which equals what? Which equals to, it implies this equals to f dash dash of a equals to negative under 3 over 2. Let's go on. When we find the third derivative of that equals to what? Equals to negative cos. We know that the derivative of sine is cos, but it's positive, but we have a negative there. Then when we multiply that, equals to that thing. So we have something like that. So it implies the third derivative we evaluate at that point, it is a negative cos of pi over 6. And how will it look like? The cos of pi over 6, we know that cos is under 3 over 2. Oh, sorry. There is a half. Negative a half. And there, we are going to have the derivative of that thing there equals what? Negative, we have a negative under 3 over 2. Let's go to the fourth one. Let's write it here. Let's write it there. So we differentiate the fourth derivative. We're going to have the fourth derivative of what? Of x. Now we are trying to find the derivative of that. It will be equal to sine. We know that the derivative of that is a thing there. So it will be sine x. But remember, it was a negative there. That means negative, once you differentiate, a negative and a negative will go. That means you're going to be left with a positive sine x. And evaluating, when that equals to a, what are we going to have? We're going to have the following. That is sine what? Sine pi over 6, and that is sine of pi over 6 is negative, positive, and that is sine of pi over 6 equals to a half. So how are we going to do that? Let's write that those values we have obtained in this form. So it will be sine of pi over 6 plus h equals to what? F of a. And where is our f of a? Our f of a is that one, is a half. Plus h, but f dash of a. What is f dash of a? Is that thing there. So we have under root 3 over 2, but times h, this one. Now let's go to the second one. It's negative a half times, so we have a negative a half, and this, remember, is multiplied by what? By h square over 2, and that is factorial. So if we try to write that much careful and that much correct, how will it look like? If you try to find the product of this, that means we're going to have the following. We're going to have a 1 over 4 times a h square times a h square. Now what about the next one? We have the third one. So what is f dash dash, this one, negative? Okay, now we have ended up there. Now let's see. We have that square, that means we are there. Let's see there, that means is a h raised to 3, h raised to 3, but the value of is negative under root 3 over 2, then h raised to 3, then we have a 3 factorial. A 3 factorial, but if you find the product of that, you will see that it is 3 times 2, and 3 times 2, we know it is 6, then it times this one will be 12. That is to say, we can write this in a very good manner. We can write that in, then it will be over 12, then h raised to 3. Then let's see the next term. We were told that as h goes to 4, h raised to 4. That is to say, let's see the last one. The last one is a half. Then a half, it will be a half, then we have a 4 factorial. And we know that a 4 factorial, if you try to use your calculator, or a 4 times 3 is 12, times 2 is 24. Then times 24 times 2, that will be 48. Then it will be plus 1 over 48 h raised to 4. So this is the expression that we are told to find. This is the expression that we are told to find. We are told to expand that as h is raised to 4. Then after that, we are told to find the value of sine 31. Sine 31. Now let's see, how can we write that? Now sine 31, I will explain it very shortly. 31 degrees equals to what? I've written like that so that I can explain much more simple. It is sine of what? That plus 1 degree. But remember, we have been given this in radian forms. That is to say, 30 is pi over 6. Pi over 6 plus 1. Plus 1. But what is 1 in radian form? If you try to convert degrees into radian forms, you can try to convert this 1 degree into radian forms. You will see you have a 0.01745. Try to convert, and then you will see it end up there. That means this is what we are trying to look. This is what we are trying to look. That is to say, we have this thing. This is our a, and that is our h. That is a, that is our h. Then this is how it looks like. Then after that, let's substitute this, because we already evaluated this. Now let's see how it will be seen there. So we have a half plus, then we have this one, 0.01745 minus 1 over 4. Then we have 0.01745 square. Then we have minus under root 3 over 12, 0.01745. Then plus 1 over 48. Then times what? 0.01745. That is raised to 4. So this is how it will look like. Now I have my calculator here, my scientific calculator. You can practice on how we can find that value. That means you are supposed to plug these as they are. So please use that much good calculator, and you can find the value of this. And make sure you obtain the value that is That is sine 31. Sine 31 is approximated, because this is the approximated value, is approximated to sine 31. If you try to find that one, is approximate to 5.1. So make some practice of your calculator, use it very much careful, and you end up getting that answer. So please try to find that and obtain that answer. Now let's see the next example. We have the next example, and we have been told to obtain the series as f of x equals to 3x squared minus 6x plus 5 about the point x equals to 1. That means you can obtain this, do it as one of the training, as one of the exercises, as one of your practices. Now let's see, what is Maclaudian series? Now consider f of x where a is equal to 0. That is to say, we have that expression that we used from Taylor's series, that expression, and now we are going to consider when a is equal to 0. That is, when a is equal to 0, what are we going to be left with? Now remember, our expression from Taylor's definition was a c naught plus c1, and this was multiplied by x minus a plus c2 x minus a square, c3 x minus a 3, and so forth, c4 x minus a raised to 4, and you can go on as where you can like. Now we are going to evaluate when a is equal to 0. Now when a is equal to 0, that's the first step. That is to say, we're going to be left with a c naught c1 x plus c2 x squared plus c3 x cubed plus c4 x raised to 4. That is to say, plus c5. You can write it as more times as you can go. Now again, we are supposed to find the value of these c's. We are supposed to find the value of those c's. Now we can find the value of those c's as we did in previous Taylor's series. But after that, we are going to evaluate when x is equal to 0. When x is equal to 0. There we used it to evaluate when x is equal to a. Now we are going to evaluate when x is equal to 0. Now let's see. Let's start by evaluating the first one. That is to say, we are going to have f of x. F of 0. That means if you put a 0, if you put there a 0, all of those will go, and you will be left with c sub naught. Now let's find the second one. That means we are going to differentiate, and if you differentiate that, the first derivative of that function, this will go, and you'll be left with that c1 plus there it will be 2x or 2c sub 2, 2c sub 2 x, then it will be a 3x square plus 4c 4x raised to 3, and so forth, plus 5c sub 5 x raised to 4, plus down to as many factors as you can. Now evaluate that, the first derivative when x is equal to a, you are going to be left, when x is equal to 0, that means this is when x is equal to 0, that is to say all of these factors will go, then you are going to be left with that one, only that one. Now let's then again differentiate that, a second derivative to that, that is to say this will go, and we will be left with 2c2 plus 3 times 2, say 3x plus 4c4, and then we have x squared, times 3 there, c4 x raised to 2 plus 5. 5 times what? Times 4 c5 x raised to 3 and so forth and so forth. Now let's evaluate that. Let's evaluate when x is equal to 0. We are going to have all of those will go, and then we are going to be left with 2c2. That implies the value of c2 equals to the second derivative of the expression evaluated at 0 divided by 2 factorial. Now let's check the third derivative of that expression. It will be 3, and if you try to look that much careful, it will be times 2 c3 plus 4 times 3 times 2, sorry, c over 4, and so forth and so forth. All of those values will be go when we evaluate at 0. We are going to be left with 3 factorial of c3. That is to say, c3 equals to what? To the third derivative factorial, and so forth and so forth. That is to say, if we try to do the next one, it will look the same. That is to say, we can predict the next one. It will be a c4. It will be the fourth derivative of what? Evaluated at 0 over 4 factorial. That is to say, if you try to plug all of those values to the expression that is what? That is there when is evaluated at 0, that is to say, at that point, what are we going to have? But remember, you have this. Then it will be what? F of x, and there we have f of 0, and then we have f dash of 0, but multiplied by x. Now I will replace x by h. That means we are going to have a h, then plus f dash dash of 0 of h square over 2 factorial plus f dash 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 of 0 h raised to 3 over 3 factorial, then f raised to 4 of 0 of h raised to 4 over 4 factorial. So this is the special case of Taylor's series. The special case of Taylor's series, and it is known as Maclaurin's series. And it is known as Maclaurin's series as when we first assume a is equal to 0, and then after that we are going to evaluate the value of the constants when x is equal to 0 again, and then you are going to be left with the series that looks like that, and that is so called Maclaurin's series. Now let's see one of the examples. Now we've been told to find the series for e f of x equals to e raised to x. Now how do we do that? Let's see. It's the same, it's quite the same. Now if the question is like that, that means you are supposed to use Maclaurin series and express that as a series. Now let's check it out. We have a few examples that requires us to the Maclaurin series. We have a few examples, and the example number 1 says find the series for f of x equals to e raised to x. Now we have f of x equals to e raised to x, and remember our Maclaurin series. This is our Maclaurin series. That means we are supposed to evaluate that function at that point, and then we go on up to there. Now our series, if we try to remind ourselves, is f evaluated at that point, then we have a h, the first derivative evaluated at that point. We have h raised to 2 over 2 factorial, second derivative evaluated at that point, and then we have a h3 over 3 factorial, third derivative evaluated at that point, and so forth. Let's say for factorial, the fourth derivative, and that is the fifth derivative of the function evaluated at 0 over 5 factorial, and so forth and so forth and so forth. That means we must have the series like that. But specifically, the series for e raised to x. That is to say, our function equals to what? E raised to x. It implies when we evaluate at 0, we are going to have e raised to 0. And we know that any number raised to 0 equals to what? Equals to 1. That is to say, this equals to 1. Let's find the first derivative so that we can find this value there of, that is to say, the first derivative of that will be e raised to x. And evaluating that at 0, that is e raised to 0 of the first derivative, we know it's 1. So let's go. The second derivative will be the same, e raised to x. So it's like some kind of a joke. The second one, that is to say, this is e raised to 0. So we have f second derivative of 0, that is 1. And then we have third derivative of x, the same still. So it doesn't change. I do hope you understand what I'm trying to explain it here. So as you can see, they don't change. So what are we going to have? Now let's put these values on those points. That is to say, we are going to have our f of x, which is e raised to x. It will be 1 plus h, this is multiplied by 1, plus h square over 2 multiplied by 1 again, then plus h3 over 3 multiplied by 1, then h4. So this goes over 4 factorial multiplied by 1, then h5 over 5 multiplied by 1. But remember, our value there was x. That means our h equals to x. That is to say, we have 1 plus x square over 2 factorial plus x raised to 3 over 3 factorial plus x raised to 4 over 4 factorial plus x raised to 5 over 5 factorial, and so forth. This is e raised to x. That is the expansion by Maclaurin's series, And I do hope you have seen this thing somewhere. Now this is how it is found by the use of Maclaurin's series. Now let's check the next example. And let's see how it will look like. Now we have the next example that says determine the value, determine the Maclaurin series for f of x equals to natural logarithm of x plus 1. We have to determine that. Now it's fairly simple and very easy. I will just leave that there. So now our function is natural logarithm of x plus 1. Natural logarithm of x plus 1. Now we have to find the derivative of those, and then go on, and then go on. Then after that, we write that in that form. How will it look like? Let's see. Now we have, that means f of x equals to natural logarithm of x plus 1, implying that we're trying to look for this. F of 0 equals to natural logarithm of x 0 plus 1. 0 plus 1 equals to 1, and we know that natural logarithm of 1 equals to 0. So this is 0. So it implies f of 0 equals to 0. Let's go to the next one. We have the first derivative. So how will it look like? Remember, this is a function of a function. That means, first of all, we differentiate that, and differentiating that thing inside, it will be the same like that. So trying to check for that, if we put there f of 0 it will be equals to 1. Then it will be 1 over 1, and then is 1. Let's go to the second derivative. Second derivative of x, this one, we're trying to differentiate it a second time. That is to say, we can use a quotient rule. And how do we use that quotient rule? How will it look like? Then we differentiate that minus, that is 0 times this one, minus, we know that quotient rule is what? If we have function like that, and then you are told to differentiate those, how will it look like? It will be derivative of f times g minus derivative of g times f, and then g is squared. So this is how will it look like. It will be 1. Okay, we differentiate that is 0 times this one is 0 still. Then multiplying by differentiating this one, it is by that way. Then differentiating this one, it will be 1 times 1 is still 1. Then this one is squared, so we have x plus 1, which is squared. Then if you evaluate the second derivative in that form, that is, you put there a 0, that is to say you are going to be left with negative 1. Let's go to the next one. Now finding the third derivative, is to be like that. And if we try to use quotient rule, as we know that we are trying to use the quotient rule, how will it look like? It will be it will come there, but remember it is a negative 2, because if you differentiate this, it will be a 0 times this thing, it will still be a 0, and we have minus, but we have negative 2, that means it will be a positive 2, and that will be 1 plus x. And remember, we are multiplying this up there. So if you try to look that much careful, it will be raised to 3. And if you try to evaluate that, it will be equal to what? It will be equal to a positive 2. And what about the fourth derivative of that? How will it look like? If you try to check it out, you will see that down up there, it will be a negative 6 over 1 plus x. Multiplying that, how will it look like? That means we square that, and remember this, the same thing is multiplied up there, so it will remain like that. So we are going to have, if we evaluate at 0, that is to say we are going to have a negative 6. Now collecting those, our series, we shall have f of x equals to what? F of 0, that is 0, then 1, that is a 1, and it is positive 1. Sorry, it is positive 1. And then again, times what? Times h. That means times h plus, but that is negative. That means it will be negative. The second one, it is h square over 2. Then the third one is plus 2 over 3 derivative raised to 3 minus 6 over 4 factorial h raised to 4 down to that. Now remember, in our question we were not given a h. That means we shall have the expansion of that function. It is a x. There is x square over 2 plus 2. Okay, if we try to simplify that, that means a 2 will go. We shall have x raised to 3 over 3. Then minus that, if we try to simplify that, it will be a 6 over 4. How will it look like? Factorial. That means we shall have times 3 times 2 times 1. This and that. Then it will be a 1 over 4. That means we have 1 over 4 h raised to 4, but that is x and not x again. So this is the expansion of that function as we are given in our example. Student, I'm going to leave you some few questions for you to practice. We have those few questions. Apply the Taylor theorem and expand the natural logarithm in ascending powers of x, of e raised to e minus x, as far as the term x minus 4 minus e, as far as the term x minus e raised to 4 is concerned. And then after that, we are going to obtain the Taylor expansion of the function x square, natural logarithm of x, that is the product, in ascending powers of x minus 1, as far as the term x minus 1 raised to 4 is concerned, and then after that find the Maclaurin series is in that nature, and then the last one will be in that nature, and we did it as we were doing in previous example, and that is your exercise for you to do. And please find a lot of questions and they are out there, and please do them, a lot more of those, and I assure you success is on your way. And please, you are still students, so please behave like students. Bye bye.